A second here to get started. We just gotta.
Okay, welcome everyone. I hope you all had a great Thanksgiving break, and hope you also get some time to catch up with colleagues during the CGD cafe. Today we have Walker Lee, our very new postdoc at NCAR, to give us a talk about marine cloud brightening and stratospheric aerosol injection. Before coming to NCAR, Walker was a graduate student from Cornell, where he studied like climate geoengineering. So he's gonna tell us a little bit more about like what he studied and some of his very interesting findings. And at the end of his talk, like we will turn on the ceiling mics so that if you have any questions, just raise your hands and I will ask you to ask your questions. Okay, it's all yours.
Thank you very much. How's the microphone coming? This sounds good. All right. Good morning, everybody. My name is Walker Lee, and I'm a relatively new postdoc at NCAR, and it's a privilege to be here giving this seminar this morning. So the agenda for today's talk. So I am not as senior as many of the people who have given the CGD seminar recently, but fortunately I did recently give an approximately 40-minute talk in the form of my PhD dissertation. So the talk I'm giving today is largely based on that. But due to the change in venue, I'm going to be spending less time talking about the nitty-gritty of my individual projects and more time talking about some introduction and research history that I think would make the talk more meaningful and relevant for the people in this room. So I'm going to start by giving an introduction, which largely addresses the question, what is solar geoengineering and why do we care? And then a few more minutes talking about the history of solar geoengineering research that informed my PhD work and sort of the current state of the literature and the research. I'll spend a few minutes talking about my PhD work at Cornell, and then a few more minutes talking about the project I'm now working on as a postdoc at NCAR, and hopefully can have this wrapped up in about 40 minutes. Introduction. What is solar geoengineering and why do we care? I don't think I need to explain the importance of these figures to anybody in this room. This was included in my PhD defense for the benefit of my colleagues in mechanical engineering and also my extremely conservative grandmother. But the world is getting warmer and is expected to continue getting warmer. And that warming is associated with various reasons for concern, and larger amounts of warming are associated with larger amounts of risk. So what can we do to stop this from happening? This is a scenario proposed in a 2017 United Nations report that describes a plausible pathway that could limit global warming to under 2 degrees Celsius by the end of the century. So we have this peak in carbon emissions, and then the difference between the 2-degree pathway and the business as usual in yellow. This green patch represents mitigated emissions, and the brown patch represents CO2 that is still being put into the atmosphere, and that's being offset by what are called net negative emission technologies, also known as carbon capture and storage or carbon dioxide removal. And in this pathway, we reach what is called net zero by about 2090 and net negative emissions thereafter. So if we look at this in terms of climate impacts as a function of time, it would look something like this. In the solar geoengineering research community, this sketch is called the napkin diagram because it was originally drawn on a napkin by John Shepard at a conference in 2009. So you can see that in this business as usual pathway, climate impacts are expected to increase with time. But if we are able to aggressively cut our emissions, the analogy for cutting emissions is like taking your foot off the gas pedal if you think your car is headed for a crash. It would be silly not to, and it stops the problem from getting worse, but it doesn't make the problem go away by itself. In order to do that, you'd want to put your foot on the brake, and that would be analogous to carbon dioxide removal, because once we reach net negative CO2 emissions, that is what would cause climate impacts to start going down. So what's wrong with this picture? Firstly, there's error bars on all of these lines, and the error bars are enormous. Not only that, but the axes of the graph are also highly uncertain. There's no units here for climate impacts or time, because the timeline and the impacts that we could expect to see are highly uncertain. Additionally, even in this sort of best case scenario, there's a couple more problems. The first problem is cutting emissions aggressively. The perceptive among you might have noted that on my graph on the last slide, the peak in carbon dioxide emissions happened in the year 2020. Emissions did drop in 2020, but that was because of COVID, and in 2021, they bounced right back up again, and that has continued into 2022. Additionally, thinking about carbon dioxide removal, the level at which carbon dioxide removal technology needs to be improved and scaled up requires a simply staggering level of technological advancement from where we are today. Going back to that to under 2 degrees Celsius scenario, you'll notice that we would need about 10 billion tons a year of carbon capture by mid-century, and then double that by 2100. And the current state of the technology, even if we took all of the different methods and lumped them together, we're simply nowhere near that level of readiness. Carbon capture is an absolutely vital part of a path to net zero, but we can't rely on carbon capture alone to get us out of the climate crisis. And personally, I think that the current state of carbon capture technology is best summed up by a headline by Business Insider from 2021. The world's biggest carbon removal plant just opened. In a year, it'll negate 3 seconds of global emissions. So in this particular diagram, the sort of most concerning part of the graph is going to be this spot in the middle where the climate impacts peak. However, the actual climate sensitivity is quite uncertain. So even if we did set a level of carbon dioxide in units of parts per million for concentration in the atmosphere, it's not guaranteed that these levels would keep us below 1.5 degrees of warming. In the last IPCC report, I believe that the climate sensitivity had, they described it as being medium confidence, which was associated with approximately a 2/3 level of confidence. And additionally, even if we do stay below 1.5, of course, that doesn't mean we're guaranteed to avoid severe impacts from global warming. Going back to the graph on the first slide, if we cut off everything above 1.5 degrees, you can still see that 1.5 degrees of warming are still associated with moderate, high, and even very high levels of risk. So in summary, we do not have a guaranteed path to avoiding the worst consequences of climate change. It is possible that emissions will stabilize and start reducing in the next few years. It is possible that the appropriate level of improvements will be made in the realm of carbon capture and storage. It's possible that that will keep us below 1.5. It's possible that 1.5 will be enough to stave off the worst of the climate impacts. But none of these are guaranteed, and the level of risk and the level of likelihood would be unacceptable in any other realm of life. So that brings me to solar geoengineering. Solar geoengineering refers to the deliberate reflection of sunlight to cool the planet. You may have heard it called by several other terms: solar radiation management, sunlight reflection methods, solar climate intervention, or simply geoengineering. The figure on the right comes from a 2021 National Academies report that focused on 3 main methods of solar geoengineering, and I'm going to focus on 2 of them in my talk today. So my PhD work was in stratospheric aerosol injection, where reflective Usually sulfate aerosols are artificially introduced into the stratosphere to reflect incoming sunlight. And then my postdoc work focuses on marine cloud brightening, which is the artificial brightening of low marine clouds to reflect sunlight analogous to the way you can see bright ship tracks in satellite photos. So a very brief history of solar geoengineering. Stratospheric aerosol injection was first proposed in 1974 by a man called Mikhail Budyko. I don't know if I'm pronouncing that correctly, forgive me if it's wrong. But originally it was considered to be a mad scientist's dream. Why would we possibly even think about doing something as crazy as this? If we're seriously concerned about global warming, we should be putting in our efforts into actually fixing the problem through mitigating emissions. However, in 2006, Nobel Prize winner Paul Crutzen put out a paper that basically said, we are too far gone to not start thinking about this seriously. Based on the way that we have handled mitigation and cutting emissions thus far, which was, in his opinion, had gone extremely poorly. I think he used the word pathetic. We're too far gone to not start thinking about it. There were first conferences in the late 2000s, a few years after Dr. Crutzen's paper came out, but it was still politically unpopular. The term solar radiation management was invented because scientists at the first geoengineering conference were not allowed to use the term geoengineering because their funders would not accept it. In today's world, there are government programs, including in the United States. My postdoc is funded by the NOAA Earth's Radiation Budget Program. And there are occasional articles in the mainstream media. You might have noticed op-eds in the New York Times in the past few years, and I'm guessing that the area will continue to grow. However, there are still some people in the world of climate science who won't even talk about it. Michael Mann, for instance, is a very prominent climate scientist, and it's his opinion that anybody who even thinks about solar geoengineering is in the pocket of big oil, and that we should be focusing on all of our efforts entirely on mitigation and carbon capture. So, how does solar geoengineering play into this napkin diagram? Well, if solar geoengineering were executed well, it might look something like this. It would be a temporary measure to reduce climate impacts until carbon dioxide levels in the atmosphere could be stabilized. And I just want to make a note that in no way is solar geoengineering a solution to climate change. It might be part of a solution, but by itself, it is not a solution, because it is not a substitute for cutting emissions and carbon dioxide removal that are the root of the actual problem. If we do not cut emissions, then the scope of the solar geoengineering intervention would have to increase indefinitely. And while we haven't quite figured out the point where it would stop working, the risks associated with solar geoengineering would get larger and larger over time. And broadly speaking, I think the vast majority of us in the solar geoengineering field consider the graph on the right to be unacceptable. So if solar geoengineering isn't going to solve the problem, then why do we study it? Well, the first is humanitarian reasons. We know that stratospheric aerosol injection would definitely cool the surface, but there would be other impacts that we still don't fully understand. But at this point, we can say confidently that it's possible solar geoengineering could be less risky than a world without solar geoengineering. As such, solar geoengineering could preserve lives and livelihoods and therefore prevent human suffering. In my opinion, humanitarian concerns by itself is a sufficient reason to study stratospheric aerosol injection and other forms of solar geoengineering, but I know that humanitarian concerns don't always make the world go round, so I would also like to bring security concerns to your attention. Solar geoengineering is not fundamentally expensive from the perspective of a national budget. To get it off the ground, you'd probably need on the order of $10 to $20 billion a year. To do it properly, you would need to, this would probably increase by a factor of 2 to 5 over the first 10 years or so as you were scaling up your intervention. But just to get it started, any medium-sized nation or a coalition of smaller nations, that kind of money would not be hard to put that in the national budget. And however, the main sort of barrier to doing this properly would be aircraft engines. There's not a lot of countries in the world that can produce the aircraft engines you would need to do stratospheric aerosol injection properly. But there's a lot of potential that this could be done improperly. This is what economists call a free driver problem, where one group of actors can affect every other person on Earth. So my question is, in 10 years, 30 years, or 50 years, what are we going to wish that we knew? Because at some point, whether it's for humanitarian reasons or security reasons, this question is going to get forced, and we need to understand how to respond. So this last point at the bottom, 10, 30, or 50 years, what is the timeline going to look like for something like this? Well, to answer your question, I'd like to point you to a startup that you may have heard of in Silicon Valley called Make Sunsets, where these two gentlemen, let's call them Tweedledee and Tweedledum, have started filling balloons with sulfur and launching them into the stratosphere. They genuinely believe that they're saving the world. They tried to interface with the solar geoengineering community. We told them to stop immediately, and they didn't stop. It is my understanding that at least at the time where this dialogue happened, their balloons did not have the proper diagnostic equipment to monitor their progress, and so there was no actual evidence that the balloons were getting to the point that they say they were going. So they were basically just floating balloons full of poison into the atmosphere. And the reason I bring this up is because this is a Slack message from my former PhD advisor showing an invitation to almost sort of bring your kid to work day style balloon launch in the park. And I bring it up because this happened on the day of my PhD defense. And so if the question is, when do we have to start worrying about this? The answer is now. People are already trying to do this, and they're not doing it responsibly, which emphasizes the need for timely research. So how do we do that research? Well, for now, almost 100% of solar geoengineering research is conducted using climate models. I think most of you in this room are probably very familiar with climate models, so I won't go into much detail here. However, there's also the potential for outdoor laboratory experiments that could inform model processes. However, there are some hiccups with that too. This is an article about SCOPEX, which I think stands for Stratospheric Controlled Perturbation Experiment, which was a balloon experiment that Harvard wanted to do, where they would launch a balloon and drop a little bit of sulfur dioxide, not to geoengineer the planet, but so that they could fly instruments through it and try and improve model processes about how sulfur dioxide reacts and moves around in the stratosphere. However, they wanted to do this in Sweden, because at high latitudes, the tropopause is lower, so it would be easier to get to the stratosphere. And local indigenous groups in Sweden objected to the experiment on ideological grounds, and Harvard eventually decided they were going to postpone it indefinitely. So for now, we are confined almost completely to studying solar geoengineering in climate models. The next part of the research I want to talk about is what's called the design space, which is that different climate intervention strategies are going to have different outcomes on the Earth system. And we call the span of possible strategies the design space. And by strategy, I mean questions like, where do we deploy the intervention? When? What time of year? How much are we going to intervene? For example, injecting stratospheric aerosols over the equator in the stratosphere would be different than injecting at multiple latitudes in concert, and that would also be different from trying to inject just over the Arctic. And that, additionally, the amount that you inject matters. You could do some kind of constant intervention where the size of your intervention doesn't change over time. But of course, global warming is not expected to be constant over time. So you might deploy some kind of increasingly large intervention in order to offset that increased forcing. But the amount that you would need is uncertain. And so you might even go a step further and employ a feedback algorithm that monitors your intervention and makes adjustments to meet some kind of climate goal. And so that's just a couple words on how the latitude of injection or the amount of injection matters. And that's not even considering other things like the background scenario. How much warming is there and how long is it expected to last? What is the start date of this intervention? How long do we plan to intervene? So you can see there's lots and lots of room for research. So I think I've explained enough that I can go through the title of my PhD dissertation and people will actually understand what it means. So I was looking at climate intervention. Specifically, all of my PhD work was on stratospheric aerosol injection. In particular, I was looking at the design space with the intention of exploring and mapping and expanding the design space of stratospheric aerosol injection. So the questions I wanted to answer were things like, what happens in climate models? Why does it happen in climate models? How much can we trust the result? What happens when we inject at different latitudes, different altitudes, and different seasons? What kind of surface impacts can we achieve? And perhaps more importantly, what can we not achieve? So now I'm going to spend a few minutes talking about the history of the design space for SAI and a couple of acronyms that you might have heard before, specifically GLENS and ARISE. So what are the options for the design space for stratospheric aerosol injection? How much do each of these things matter? So the first question is, does the amount matter? Yes, of course it matters. More sulfur dioxide means more aerosols, which means more cooling. Broadly speaking, an intervention of about 10 teragrams per year will give you approximately 1 degree Celsius of cooling, although there are nonlinearities at larger injection rates, as aerosols will be more likely to coagulate, which reduces their lifetime. Does the latitude of injection matter? Absolutely. I talked about that a minute ago, where injecting at different latitudes will have different impacts on the climate. Does longitude matter? As of right now, it does not. East-west transport is too fast in our climate models for the way that SAI is currently implemented. So if you wanted to inject at the equator, it wouldn't matter whether you injected over Brazil, Central Africa, or the Philippines. The results would be indistinguishable in a matter of weeks. I do want to say there's a caveat that with model improvements for how aerosols are represented, once we start making more progress in incorporating things like plume models with Lagrangian tracers, it's possible that that could open up this particular dimension of the research. But as of right now, pretty much all of our experiments, we just inject over the prime meridian at whatever latitude we are choosing to inject at, because the longitude doesn't matter. Does the altitude of injection matter? This is more of a logistical consideration than a climate-based one. Injecting at a higher altitude would be exponentially more expensive, say 5 kilometers above the tropopause as opposed to 1 kilometer above the tropopause. But it would give the aerosols longer lifetime, which means you could achieve more radiative forcing for a given amount of SO2. And the last question is, does the season of injection matter? And the answer is it matters more at high latitudes. The reason is near the equator in the tropics, you get approximately the same amount of sunlight year-round, but at the poles, you're only getting sunlight in half the year. And so if you have reflective aerosols in the half of the year where you're not getting sunlight, those aerosols aren't doing anything. And so the timing of your injection matters a lot more the closer you are to the pole. So some of you may remember this figure from the CGD Day of Discovery a couple weeks ago. This is what is called a block diagram, which is one of the fundamental aspects of feedback control theory. It looks quite complicated, but it's in concept, it's pretty simple. And feedback control is pretty ubiquitous in everyday life. A common example would be something like a thermostat. You have some desired reference value, maybe a comfortable 22 degrees Celsius for your living room. And the state of the system is measured by some kind of measuring element, which would be a thermometer incorporated into your thermostat. Based on the difference between your actual room temperature and your desired goal, the thermostat will send a signal to your radiator to try and correct that difference. And even in the presence of disturbances or uncertainty, maybe you have leaky windows, poor insulation, someone's going in and out of the front door and the cold air is coming in, a well-designed controller can maintain the reference value in the face of disturbance and variability. And about 10 years ago, my PhD advisor, Doug McMartin, was one of the people who pioneered the application of feedback control theory to stratospheric aerosol injection. So in this case, the system is your climate model, and the measuring element is your model output. You set some kind of climate goal. Maybe you want to stabilize to a desired global mean temperature. And then after the model runs, you have a Python script compute how much stratospheric aerosol you want to inject. And then even in the face of natural variability, a well-designed controller can maintain your desired climate goal. And so feedback control has become sort of a staple in the climate engineering field in order to, rather than just injecting a certain amount and seeing what it does to the Earth system, we employ more of a top-down design process where we specify a climate goal, and then the feedback algorithm chooses how much to inject and where. So just a little more on how we actually implement that for the climate model nerds in the room. So this is a single line in the name list of CESM that specifies, we have just a net CDF file that specifies how much sulfur dioxide we want to put in. We multiply that by a scalar, and the net CDF file has the altitude, latitude, longitude grid boxes, as well as a dimension for what months of the year we want to inject in. And we just plop this into the external forcing in user NLCam. We run the model for a year, and then the Python script compares the performance of the model to the goal and goes back and modifies the name list. And it turns out this process actually does a really good job at regulating global mean temperature. These are some of the first simulations that my advisor did with Ben Kravitz at Indiana University. And in this high warming scenario, RCP 8.5, they were able to maintain the desired global mean temperature out to 2100, despite the increasingly large amount of warming by the end of the century. However, we can go further than that and meet multiple goals at the same time. If we have multiple outputs, then we need multiple inputs. And they found that by injecting at these 4 different latitudes, if our input is the zonal mean aerosol optical depth, then we can control 3 aspects of the zonal mean aerosol optical depth independently. If you're unfamiliar with the Legendre decomposition, these are the first 3 Legendre polynomials mapped onto sine of latitude. And basically, L0 represents the global mean, L1 represents the balance between the northern hemisphere and the southern hemisphere, and L2 represents the equator to pole balance. And by managing these 3 degrees of freedom independently, they were able to control what we call T0, T1, and T2, which is temperature mapped onto that same truncated Legendre polynomial. And this became the precursor to the first geoengineering large ensemble. So the last thing I want to talk about before my actual research is the current state of the SAI design space. These are the 2 large ensembles of solar geoengineering that have come out, and Glenn's came out around the time that I started my PhD, and Arise came out around the time that I finished it. So I've sort of been growing with the field over the last 5 years or so. So GLENS stands for Geoengineering Large Ensemble. It was conducted in about 2017 and 2018, and it used CESM1. The targets were T0, T1, and T2, and the specific targets were an average of a certain time period. And it used the RCP 8.5 background and ran all the way through the end of the 21st century. And the reason is, the goal when designing this experiment was scientific relevance. We wanted a really, I shouldn't say we, I wasn't there, but they wanted a really high signal to noise. So they ran 20 ensemble members with this extremely high warming scenario all the way out to the end of the century where there's 4 to 5 degrees of warming so that they could get a really good signal for determining what did the aerosols actually do to the climate. And about 5 years later, folks at NCAR conducted the first experiments as part of the Arise initiative. These were called Arise SAI 1.5. And so these were conducted in 2021 to 2022 and used the newer version of CESM at the time. And I wanted to note that they had the same temperature targets. So the choice of what aspects of the climate to control did not change over that 5-year period. And that means that this T0, T1, T2 controller is sort of the gold standard for climate intervention research today. But they, instead of using RCP 8.5, they used one of the new SSPs, and they used one of the more moderate warming scenarios on what they considered to be a more realistic timescale. Obviously, 2020 has passed, and we haven't started geoengineering yet. But the goal for Arise SAI 1.5 was to be more policy relevant, using what they considered to be a more realistic warming scenario and timeline to have more policy relevance than the original GLENS experiments. So these came out, I was actually a co-author on the Arise paper, came out, I think, last summer. And so that's a good segue into my own PhD work, which focused on answering the question, are there other goals we can meet? And how can we meet those goals? So the first project I did is if we have 3 degrees of freedom, L0, L1, and L2, we could visualize this as a 3-dimensional space. And only part of that space is actually attainable in a climate model for reasons that I'm not going to go into right now. But one thing we can do is we can visualize a desired climate goal as a surface within that space. For example, if you care about some change in global mean temperature that is brought about by your stratospheric aerosols, it turns out that where that aerosol optical depth is located is less important than just how much of it you have in the first place. And so we can visualize our global mean temperature goal as a planar surface that is perpendicular to the L0 axis. And depending on where you're operating within that space, you can know whether you can expect to overcompensate your climate goal or undercompensate it based on how many aerosols you're actually putting in. And based on whether multiple climate surfaces in this model intersect or not, that can help you figure out whether certain climate goals could or could not be met simultaneously with this injection strategy. So, for example, here are 3 surfaces where we have the orange triangle represents a global mean precipitation goal. The red triangle is the location of the intertropical convergence zone. And SSI stands for September sea ice in the Arctic. And so you'll notice that if we're operating on the intersection of the red and orange triangles, there's an intersection there, but it's not enough L0 to bring back sea ice to the desired extent. And so we did a simulation where we tried to meet 3 goals at the same time, and we met our precipitation goals, but we didn't have enough juice left in the tank to bring back September sea ice. We did another simulation with 3 other targets, this time using global mean temperature instead of precipitation. And if we're operating at this intersection between temperature and stabilizing the ITCZ, you're actually injecting too much for your desired amount of sea ice that you want to bring back. And so doing the same thing, we see that the amount of sea ice at the end of the simulation is more than we told the controller to bring back. And so the takeaway of this is that we can visualize and quantify the trade-offs of solar geoengineering. Any climate goal is a compromise. Solar geoengineering, and SAI in particular, is not a hard reset button for the climate. You're creating a new climate state, and it's important to keep that in mind. So these are all the different climate goals we looked at in the paper, and how much solar geoengineering and where you might need in order to meet them. A few other projects I did looked at high latitude SAI, focusing on the Arctic. I think I'm running a bit low on time, so I'm going to skip through this a bit faster. So there were a couple of assumptions when we looked at Arctic sea ice in these studies. First, only injecting in the tropics and mid-latitudes, and also injecting year-round. And this was sort of the norm at the time. The first Arctic SAI experiment that I could find dates back to 2008. But as I mentioned a little bit ago, if you're injecting at high latitudes, you might want to consider injecting seasonally, because once you start to get inside the Arctic Circle, you're going to see many times more sunlight in the summer months than you are in the winter months. And so if you have some amount of SO2 injection spread out evenly through the entire year, you're going to have a slight peak of aerosol optical depth in the summer because there's more sunlight to produce more OH, which means you're going to get more oxidation from SO2 into H2SO4. However, the seasonal cycle is relatively small. You're still going to have a lot of AOD in the winter months that's effectively wasted. But what if you took the same amount of SO2 and loaded it into the spring months so it can oxidize in time for summer? And you're going to have a peak that coincides nicely with the maximum sunlight in the winter months, in the summer months. And so if you look at what that actually looks like, we compared year-round and spring injection at 60 degrees north, and you can see you get much, much more concentrated aerosol optical depth in the summer months if you inject just in the spring. And then if you look at the impacts on the actual Earth system, you bring back about twice as much Arctic sea ice during that time period. And I just really love the pretty graphs of sea ice coming back. So a couple of those as well. So with this experiment informing our understanding of the design space, we did another larger experiment where we wanted to directly compare spring injection in the Arctic with the sort of standard T0, T1, T2 global strategy. And this was sort of my flagship PhD project. And so we had 3 experiments with global 1.5 is kind of the default. It's the same as a RISE, just in a slightly less expensive version of the same climate model. And then we did 2 more experiments, which injected about 33% more and about 33% less, but just in the Arctic. So the global strategy, most of the injection was actually in the southern hemisphere. The controller decided that most of the injection needed to go at about 15 degrees south. Whereas the Arctic strategy was focused on 60 degrees north in the spring. A couple of interesting results from that. So first, Gunter, our friend in this department, helped us look at the Greenland ice sheet. The Greenland ice sheet has 2 big ways that you can look at how it might change under climate change. The first is called surface mass balance, which is the net sum of precipitation, evaporation, and runoff at the surface of the glacier. and the other is large-scale ice dynamics, glacial calving, elevation changes. The latter was not implemented in the version of the climate model we used, but we can still look at surface mass balance. And the graph is quite messy, but looking at the Arctic high simulation, we see that we substantially increased the surface mass balance of the Greenland ice sheet over the course of our experiment. And breaking that down into its constituent components, we see the main reason that the main reason for the change is reducing runoff at the edges of the ice sheet. We also looked at permafrost, which Dave Lawrence helped us out with. Per Dave's advice, we measured permafrost by looking at what is called the active layer, which in permafrost regions is the topmost region of the soil, which thaws out in the summer and freezes in winter. So if your active layer stays small throughout the entire calendar year, that means you have a large chunk of frozen soil underneath, and that means more permafrost. So we looked at the area in the mid to high latitudes where the active layer stayed at less than 3 meters year-round, and our Arctic high experiment substantially increased both the thickness of the permafrost layer and its extent. But we also, I bring this up because I wanted to note that this doesn't tell the entire story. CESM2 does have permafrost carbon as one of its outputs. And while permafrost carbon modeling is still very uncertain, we can still look at it. And we see that we do see modest increases in soil carbon in the permafrost region, as to be expected. But there's another permafrost stock in the mid to high latitudes, and that is vegetation. Vegetation in these areas would actually enjoy the warmer, carbon-rich environment from global warming. And if you take away that warming, you're going to take away the happy plants. And so in this simulation, the change in vegetation carbon was much larger than the change in soil carbon. And so in the short term, you're actually going to decrease the effectiveness of the Arctic as a carbon sink as a whole. Now, someone who knows more about permafrost than me could interpret the significance of these results. But it's important to bring up that solar geoengineering doesn't always do what you want it to do. Sometimes the impacts could be considered negative, and that's something we have to understand. And then lastly, even though we injected at 60 north, the effects are not contained to the Arctic. You're cooling almost the entire northern hemisphere, and also you're shoving the ITCZ a good few degrees to the south. And so that means that any injection in the high latitudes of one hemisphere would almost certainly have to be balanced by an injection in the other hemisphere to stop this from happening. Briefly, the last graduate project I looked at was why does injection altitude matter? Injections at different altitudes had similar surface impacts. We looked at injection just above the tropopause and then about 5 kilometers above it, and the temperature maps are virtually identical. However, the low experiment needed about 2/3 more SO2 injection to meet the same temperature goals. So we wanted to break down exactly why that happens. So with a little decomposition, you can examine the ratio of AOD per unit injection rate, which is going to be governed by the lifetime and sizes of the aerosols. And then we also looked at the cooling achieved per unit aerosol optical depths, which is going to be governed by radiative feedbacks. And the only difference between these two particular simulations was what we call the water vapor feedback, which is where if you're injecting close to the tropopause, you're going to bring more water vapor into the stratosphere. Water vapor is a greenhouse gas, and in the stratosphere, it's going to have a longer lifetime, which means that you're increasing the greenhouse effect, and that's a negative feedback against your stratospheric aerosols. And so because these two experiments have the same amount of cooling, any differences in injection rate must be balanced by differences in these two factors. And so if we plot them for each of the two experiments, we find that overall the lifetime and size factors had a much bigger contribution to the reason why the ILO experiment was so much less efficient at managing global warming. And so briefly, a few minutes talking about my current work at NCAR. All of my PhD work was based on stratospheric aerosol injection, but my project at NCAR is actually looking at marine cloud brightening and attempting to build the first feedback controllers for marine cloud brightening interventions. So work that my supervisor, Jack Chen, did last summer is looking at purely based on radiative efficacy, what are the most susceptible regions of the ocean that you might want to seed in order to reflect the most sunlight. And so these maps indicate in different months of the year, the darkest shade of purple are the single most susceptible grid cells, and then If you're looking at the top approximately 5% of the ocean, that's going to expand to include the yellow regions. And then if you're looking at the top 10%, that's going to go all the way out to the regions marked in red. And what Jack did is he did experiments seeding different percentages of the ocean area for 35 years, the same timeline and background scenario as the ARISE SAI runs. So Jack's driving question is trying to figure out approximately how much of the ocean would you need to seed in order to meet the same kind of temperature goals we're looking at with SAI, that is limiting global warming to 1.5 degrees above the pre-industrial. And oops, that's supposed to come in later. If you look at the changes in temperature for each of these experiments, this is actually enough information to build a working feedback controller, where if you're injecting smaller amounts, you have less cooling, and if you're seeding a larger portion of the ocean surface area, then you have more cooling. I'm going to skip the sea ice graph for the sake of time. So what we did is, after I started at NCAR, we built the first ever MCB controller where we expanded the coverage of marine cloud brightening to cover a broader ocean surface area over time, with the hopes of meeting the same temperature goal as ARISE SAI 1.5. And so the first controller that we did is what we call just a feed forward, where we prescribe the increasing intervention over time. And it did a pretty decent job of reaching the 1.5 degree temperature target by the end of the simulation. But of course, we can do better than that. So we did 5 more ensemble members where we turned the feedback on. And we can see that that did an even better job of limiting global warming to 1.5 degrees above pre-industrial. So where do we go from here? This is a graph of the surface changes for the ARISE SAI experiment relative to the background that they were controlling for. And you'll notice that almost the entire graph is white, which means that the surface temperature map under the geoengineering scenario is almost identical. AMOC is doing some weird stuff in the Northern Atlantic, but other than that, the temperature map is pretty similar to the background pre-warmed environment. But if we look at the 1 degree of freedom MCB controller, we see that that's absolutely not the case. Now, this can be reasonably expected because by the end of the experiment, we're seeding 6 to 7% of the ocean area. If we're only seeding in this part of the world, then we're going to see overcooling in that region and undercooling or even warming in other parts of the Pacific. So the next projects that I'm working on is, can we improve this temperature map to look a little more like this temperature map by managing the areas of the ocean that we seed more effectively. And instead of controlling purely for susceptibility, can we also control for regional climate outcomes? And the ultimate question is, how close can we get marine cloud brightening to the sort of state-of-the-art stratospheric aerosol flagship experiments? So wrapping up, where do we go from here? And there's really one big question that I get asked a lot. And the $1 million question is that's my 40 minutes, is stratospheric aerosol injection or marine cloud brightening, is it a good idea? Do I think it's a good idea? And I want to say, I think that question, the premise of that question is wrong, because we do not have the luxury of asking ourselves, is this a good idea? We do not have 500 years to improve our climate models and then get everybody on Earth into a big room and talk about it for a while and decide, do we think that a little bit of solar geoengineering would make the planet a better place to live or a worse place to live? Because we need to weigh the risks of geoengineering against the risks of global warming. Because like I said earlier in my talk, someday this is a question that's going to be forced. And in a way, this makes geoengineering research almost an impossible quest, because we're never going to get to the point where we fully understand it, but we need to be able to make the best informed decisions that we can in order to provide the best life for everybody who shares this little blue planet with us. So I'd like to close with a quote at a conference last summer from my collaborator, Wade Smith. It's impossible quests that are the best quests. So thank you very much for your attention, and I hope you enjoy the talk.
Thank you so much, Walker. A lot about solar engineering. Any questions in the audience? Okay, yes. Is the mic turned on?
Yep. We good to go?
Okay, yeah, we're good to go.
I was wondering, About the effect of the stratospheric injection on plant life and solar panels.
That is an excellent question. The short version is that the impacts wouldn't be huge, and the reason is solar geoengineering with stratospheric aerosols that cooled the planet by about 1 degree Celsius, you'd only need to reflect about 1% of sunlight in order to do that. There have been studies on this, and it's possible that with solar geoengineering you get less direct light but more diffuse sunlight, and it's possible that plants could like that even more, and that solar radiation management with stratospheric aerosols could actually improve crop productivity. But regardless of that, the impact of heat stress on plant growth is going to be many orders of magnitude more important than the amount of direct or diffuse sunlight they get. And so by reducing that heat stress, you can improve crop yields. The exact amount of cooling that you'd want would depend on the plant and the region of the earth that it grows in. I think the folks at Rutgers are doing some work on that. But we would not be blocking out the sun. We wouldn't be shutting off all the plants or shutting off all the solar panels with a 1 degree intervention.
Okay.
So I didn't hear you mention that this SO2, when it falls out, increases the rate of acidification in the ocean, which is probably going to be a significant problem.
So to talk about, as my advisor liked to say, what goes up must come down. And anything that you're putting in the stratosphere as SO2 is going to come down either as SO2 or H2SO4. One of the big problems with stratospheric aerosol injection is that it doesn't stop ocean acidification, and in fact would contribute to it, which is why SAI is not a substitute for mitigation. Now, the actual amount of sulfur that we'd be putting in the stratosphere is probably not as much as you'd expect. Based on current rates of sulfur pollution, a 1 degree intervention would probably increase sulfur pollution by about 10%. So we'd only be putting into the stratosphere about 10% of what we're already putting into the troposphere and stratosphere through pollution. And pollution is expected to decrease, sulfur pollution is expected to decrease throughout the century as we implement tighter controls. And a 1 degree intervention would probably set us back 20 to 40 years in terms of controls on sulfur pollution. In terms of the actual impacts on ocean acidification, I am not qualified to talk about what that would do to the ocean ecosystems or wildlife or anything like that.
Okay, yeah.
Okay, well, great talk. Really glad you're here and it's exciting to work with you. The one thing I wanted to sort of maybe bring up and get your perspective on is model uncertainty. Like, so you're using CSM, but I know that with the RISE simulations, when they had GEM models used, like Jim Hayward's work, they use twice as much sulfur to get the same temperature response. And so if this is the only tool we have right now for understanding geoengineering or solar radiation management, where does the model uncertainty come in? You know, that's a big element into it.
Well, ideally we live in a world with no uncertainty. And we would know exactly what was going to happen and when it was going to happen. And we could decide, is this very certain strategy of putting sulfur into the stratosphere going to make life better or worse for everyone on the planet? The bottom line is we can try to reduce uncertainty, but we will never eliminate it, and we simply have to use the best tools we have. So maybe CESM says you have to put in 10 teragrams to get 1 degree of cooling. Maybe HADGEM 2 says you need 20 teragrams to get 1 degree of cooling. And my response to that is kind of, it sucks, but we're stuck with it. Because ultimately climate models are currently the only tool we have to simulate a planet-wide intervention. And so the best thing we can do is try and understand why the two models behave differently to try and reconcile those uncertainties. But kind of like I talked about on the last slide, it's an impossible quest. We'll never fully resolve all of those uncertainties before the question is forced by someone or something. It's not a very satisfying answer, but I think that's the reality of where we are right now.
Okay, we have Jerry, and then we go to the question.
So not knowing a whole lot about this, I was just curious in terms of the technologies involved. You said you fly aircraft around in the stratosphere for SAI, but you talked about seeding for MCB. What would would the seeding technology be?
Probably ships spraying sea salt into the low marine clouds. You could probably do it with planes, but I think it would be cheaper. The actual deployment technology is that's not the biggest barrier because we don't currently have we currently don't have planes that can carry payloads of that size into the stratosphere simply because we've never needed them. Building them would not be fundamentally hard as long as you had access to the resources. And I think likewise with marine cloud brightening, once we figure out what size and distribution of aerosols would be needed to actually brighten the clouds instead of darkening them, I think it would not be that difficult for the construction of fleets of ships that would spray aerosols of the appropriate size into the clouds. Basically, ship smokestacks are already doing it. So we would just have to replicate that in a slightly more environmentally friendly way.
All right, we have a few questions online. So the first question is from David Schneider. So he asked if you could comment on Dr. James Hansen's arguments that we have already inadvertently done solar engineering through aerosol from fossil fuel burning, and B, should pursue marine cloud brightening over the Southern Ocean since the Southern Ocean clouds are a larger lever on the climate sensitivity.
So I'll address those two questions independently. Firstly, Dr. James Hansen's arguments that we've already inadvertently done solar geoengineering. In my opinion, it doesn't matter. I would use it as a counter argument to people who argue that we shouldn't be messing with nature and they're opposed to geoengineering on more philosophical grounds. I would argue that we don't have the luxury of making that kind of distinction because we've already been geoengineering the planet for a couple hundred years. So I don't think that there is anything intrinsically or morally wrong about intentionally trying to change the environment that we live in. Regarding the second question, should we pursue or at least intensively research marine cloud brightening over the Southern Ocean? Well, certainly I'm on board with intensive research. As to whether or not we actually should pursue it, that depends on what the climate impacts are going to be. But those last couple of slides that I showed with the surface temperature maps from our 1 degree of freedom marine cloud brightening experiment, I think living in that world would not be significantly better for a lot of people than living in a world with just global warming. And so if you only do geoengineering in one part of the world, there's going to be ripple effects to other parts of the world. So I'm certainly not opposed to it, but I think just geoengineering in one part of the world, whether it's SAI or marine cloud brightening, I think we need to really understand what we're doing. And in my opinion, based on my experience, it's more likely that a global project would have better climate impacts. I know better is a very loaded word, but I think that a more even distribution of cooling would result in anybody would make it less likely that some parts of the world get a much shorter end of the stick, if that makes sense.
I think that's related to Nan's question.
Yeah.
That's about practice. Like
So-
how
How do we come to consensus on geoengineering strategy? Who gets to decide? I want to preface this by saying that I am a physical scientist, and for every person looking at the physical science aspect of the problem, there was somebody else working on the social science aspect of the problem. Solar geoengineering, whether it's SAI or marine cloud brightening or something else like a big space mirror or trying to thin cirrus clouds, is a huge ethical can of worms. Because I called it a free driver problem where one actor or a small group of actors could theoretically affect every person on the planet. In a perfect world, this could be done, the word we use is legitimacy, where the people who make the decisions are represented by a large group of people, of common people. I think the closest thing we have to that right now is probably the United Nations, but even they don't represent the entire Earth's population. And if two people in Silicon Valley, for instance, decide to go out and start launching balloons, that's certainly not a legitimate intervention, regardless of how many people are buying cooling credits on their website or whatever. It's the question of who gets to decide is from an idealistic perspective, the ideal answer is everyone. From a practical perspective, the question who gets to decide is whoever decides they want to go out and do it, they've already decided. And then everybody else has to decide what do we do about it. There is no good answer to that question. And there are a lot of very smart people trying to figure out what kind of policy frameworks do we put in place to try and make sure that if and when this happens, is it going to be done ethically and legitimately? But it's messy. It's so messy.
Okay. Do we still have time?
I'm happy to answer any more questions.
Okay, yeah, go ahead, John. And then Steve.
I did, my original question was, you've sort of already asked it around sort of model biases and challenging model space, but actually linked to that, if you think, focus on this response about doing things more globally because it would be better. What, if you think about climate variability and some of the different modes of climate variability, and maybe one's linked to the stratosphere, like the QBO and sort of stratospheric warming and things that have quite significant impacts. Do we have the capability and ability to begin to understand the potential impacts on those and the people looking at that?
Well, I think you would have to ask the people who better understand how those modes of variability are represented in climate models. Personally, the experiments that I've looked at so far, the longest one that I think I've ever seen is Glenn's, which was 80 years. And that's not a very long time on timescales of climate. And so if we want to figure out the longer term impacts of a solar geoengineering intervention, we need to run the model for longer. And, that takes a lot of computer time. I know stratospheric aerosol injection is usually done with WACM, which is something like 25,000 core hours per year of model output. And I know that Simona Tilms over in ACOM is trying to do something with PI control and the one-time gradual CO2 increase and using solar geoengineering for that. And that might be more of like 150 years of model time. But that's still, maybe some of the experts even in this room could answer the question better than I could of how well equipped are we to understand the impacts of solar geoengineering on a mode of variability. I know that people were trying to look at ENSO, but in order to understand how solar geoengineering could affect a mode of variability in a climate model, that mode of variability has to be well represented in the climate model in the first place. And I know that we're trying to look at AMOC, but we don't fully understand why AMOC is behaving the way it is in climate models, which means that we don't fully understand the changes that solar geoengineering would affect on AMOC. And I know that some people have looked at specific modes of variability like the North Atlantic Oscillation. If there's a teleconnection, if you specifically geoengineer one end of the teleconnection, can you influence the other end of the teleconnection? The answer is possibly. I don't know a whole lot about that particular research, but I think the bottom line is that we have a long way to go.
Steve, do you want to comment on this about variability?
Yeah, that's my question. So first of all, great talk. So you mentioned that ARISE is kind of geared towards policy relevance, and you showed the ability to maintain stable global climate pretty effectively. But if we get to the point where we have to resort to geoengineering, you can envision that, say, the UN, if that's the legitimate body, would want to run a test. And so what would be the signal to noise that you would expect from a climate model from, say, a 1-year test of geoengineering? How long would you have to monitor before you could say with confidence it had the effect that we thought it would?
That's an excellent question. And there are two comments I want to make. The first one is another reason why geoengineering is done almost exclusively in climate models is because you can't test it. Once you are deploying enough that you're actually impacting the surface climate, that's not a test anymore. You're actually deploying it, and then you're committed to either seeing it through or slowly phasing it out in the hopes that the warming that you're masking doesn't come back faster than it would have in the first place. The question of how quickly would we be able to detect that it's happening, the answer is not fast. After a single year, unless you were hitting the climate system really, really hard, for example, sea ice responds really quickly to changes in forcing at high latitudes, but it's also extremely variable. And separating out the signal from the noise after only 1 year of deployment would be impossible. After 5 years, you might see a signal and you might be personally confident that it's because of the aerosols, but proving it statistically would be very hard in most regions of the globe. The short version is that you're not going to be able to prove it's doing what you want it to do on such a short time, and that's another problem. My PhD advisor was actually sued when I was a grad student by a complete nutcase conspiracy theorist in California who thinks that chemtrails are geoengineering and that it's already happening. And the bottom line is that what's going to happen is if we start a global SAI intervention, then the next year there's going to be a hurricane somewhere, and every nutcase on the planet is going to immediately blame that hurricane on solar geoengineering. Because even if cooling the planet might make extreme weather events less likely, it's impossible to separate the signal from the noise after 1 year. And so that's if you're going to plan a project like that, you can't, a 1 year test to see if it's working is not realistic. You're gonna have to go all in from the start at a bare minimum 5 to 10 years and be prepared to go for much longer.
Okay, yeah, we are already running. Come closer.
Oh, I don't think they can hear you. Can you?
Sorry, yeah, we're already past like 12, so there are more questions, but you can email Walker if you have further questions. Let's thank Walker again for his